sorry. I'll start over. Okay. Morning, everyone. My name is Junwei San. I'm from Simon Fraser University, Canada. The topic of my talk is shift sliding and StepStop for 3D positioning. This is a paper I wrote with Wolfgang and Dmitri. So here's an overview of my work. So moving object is an important task in 3D user interfaces. And 3D positioning is especially hard with 2D input devices, as the 2D input has to be mapped to 3 degrees of freedoms. In this paper, we present 2 new efficient 3D positioning techniques, and they are designed for 2D input devices, such as the mouse. With shift sliding, we extend sliding to floating and colliding objects. With StepStop, we address the depth ambiguity inherent in sliding, and we did the comparative evaluations on both of the techniques. So there has been a lot of previous work that focused on 3D or 6D input for object positioning. However, the virtual hand techniques are limited in range of the user's arm. And recasting is mostly a 2D input method. So 3D input is out of scope of our work, as they typically don't provide the same level of accuracy as the mouse. Multi-touch mappings requires learning and may not be intuitive for novice users. There has been a lot of techniques that are designed for 2D input devices. 3D widgets has been widely used in a lot of commercial softwares, and snap-dragging, object associations, and magnetic metaphor are all early forms of sliding. The sliding algorithm presented in 2005 was shown to be more efficient than 3D widgets for in-contact conditions. However, with the original sliding algorithm, there's no way to move the object along the line of sight. So there are 3 basic assumptions for the basic sliding algorithm. The first assumption is that the object never floats. So this is based on the observation of the real world, as floating objects are rare in the real world. The second assumption is that objects do not collide. And the third assumption is that the manipulated object is always visible to the user, and the user cannot manipulate objects that are completely invisible to them. This is a figure that illustrates basic sliding. So the user can select the object at position A and start sliding it along surface 1. So the user can slide the object along the surface 1 to positions such as position B. But if we move the cursor further upwards from position B, the object would become floating. And in this situation, we snap the object back to position C, which makes it in contact again with surface 2. And then the user can keep sliding the object to positions such as D and E. So if the user keeps moving the cursor downwards from position E, the object will become completely invisible because it will be occluded by surface 1. In that case, we pop the object to the front, so the user can see the object again, and then the user can keep sliding the object on surface 1 again. So this is a video that shows basic sliding. So with basic sliding, the object slides on the surface behind it, and it is popped to the front if it becomes completely invisible. So this is essentially a re-implementation of the work from 2005. Okay, so sliding is great for objects in contact, but how about these situations? So in the left image, we can see there is a levitating globe. in which the globe is apparently floating above the floor. In the second image, there is a drill, which is clearly in collision with the object below it. So since basic sliding cannot deal with floating or colliding objects, we introduce shift sliding. With shift sliding, the user can move the object. Orthogonal to the sliding plane by holding down the Shift key and moving the mouse. So with shift sliding, the user can break the contact assumption or cause collision. So shift sliding is basically a form of context-dependent manipulation depend on the last contact of the object on the sliding plane. So this is a video that shows shift sliding. The user can lift the object to float. If it collides with some other surface, we transition back to original sliding. The user can also push the object inside to make collision, but if it becomes completely invisible, we pop the object to the front so the user can see the object again. So here the object will become invisible. And then we pop the object to the front. All right. So in the first image row, in the first image row, the user lifts the object to float and continues sliding when he or she releases the shift button, and keeps moving the cursor. When the object starts colliding with another surface, we transition back to the original sliding mode. In the second image row, the user forces the object into collision and continues sliding. If the object becomes invisible, we pop the object to the front so the user can see it again. So sliding is essentially a 2-degree of freedom technique, as the object movement is constrained by the sliding plane. But how about if we want to move along the object in the 3rd degree of freedom? Well, in these two images, the two object positions in depth have exactly the same cursor position. Although it is possible to move between these two positions by the original sliding using this green path shown on the main, using this blue path shown on the images, but the slide around action was already identified as non-intuitive in the studies of 2005. So this is a video that shows StepStop, which is our new technique. As you can see, there are 3 possible positions to place the object in depth. So all those 3 object positions have the same cursor position. The user just have to move the mouse wheel away from or towards himself to perform the push to back or pop to front. So with StepStop, we map the mouse wheel action to move the objects in depth where the object is in contact, visible, and collision-free. So in these 4 images, there are 4 possible positions to place the object, and all the 4 positions have the same mouse position. So the user just have to move the mouse wheel away from or towards himself to trigger the push to back or pop to front. Here's a slide that shows the push to back algorithm. First, we conduct depth peeling to identify the scene layers. And for every pixel that the object and the scene overlap, we calculate the depth difference between the object and the front surface of the scene. We perform an interval test to see if there is space to fit the object to that layer, and we merge the intervals across all the pixels. The minimum solution becomes our push to back distance. And for pop to front, it's the symmetric algorithm as push to back. For concave objects, we have to loop over all the depth layers of the object, and finally find a minimum solution. Here I will talk a little bit about the performance of our system. So we use the graphics software for most of the computations, and our system works stably at 60 frames per second with 100K polygons. So the first video shows object sliding on a point cloud, and the second video shows depth pop in a complex scene with multiple layers. So we performed the evaluation for shift sliding. So in the work of 005, they have proven that for objects in contact, sliding outperformed 3D widgets. So we did a pilot study that confirmed this result. So the average time for sliding is significantly lower than 3D widgets. So therefore, for our user study, we only examine the manipulation of floating objects. So in the first user study, we used 12 participants. 5 of them are female, and the task was object positioning for floating objects. We had a 2x2x2 within subject design, and the 3 factors are 2 techniques: 3D widgets versus shift sliding, 2 display conditions, 1 view versus 4 view, and 2 target alignments, aligned versus rotated. So the target position was either aligned with a world coordinate system or rotated relative to it. So this is the video that shows the condition of widgets, 4 view, rotated. So in the 1 view condition, we only show the bottom left image, the perspective view in full screen. So we don't in the one view situation we do not have the 3 orthogonal views. The target object position is rendered as transparent, and in this case, the target position is floating above the floor. Here is a video that shows the same task with shift sliding. So this is shift sliding 4 view rotated condition. So here is the result in terms of time. As you can see, we got significant effect for all the 3 factors. So shift sliding is significantly faster than widgets. One view is significantly faster than 4 view, and the line condition is significantly faster than rotated. So for target distance, we only get significance for the display condition. So the 4 view condition has a significantly smaller distance than the 1 view condition. So in the second study, we try to evaluate shift sliding with depth pop enabled. So again, we have 12 participants. We have a 2x2x2 within subject design, but the task here is object positioning for objects in contact. So the 2 techniques becomes widgets and shift sliding with depth pop enabled, and the rest of the conditions are the same as study 1. So this video shows the depth pop 4-view rotated condition. So as you can see, the target position is around the pillar. So with shift sliding and depth pop, the user just had to slide the torus in front of the pillar and then perform a push to back. This is the same task with widgets. So this is widgets 4-view rotated condition. Here's the result in terms of time. Again, we get significance for all the 3 factors. So shift sliding with depth pop is faster than widgets. 1-view is significantly faster than 4-view, and the aligned condition is significantly faster than the rotated condition. So in terms of distance, shift sliding with depth pop enabled has a significantly smaller distance than widgets. And again, 4-view has a smaller distance than 1-view. So here's some more discussion about the results. So shift sliding is faster than 3D widgets even for floating objects. And shift sliding is at least 29% faster for rotated objects. And in a single perspective view, shift sliding is never worse than 3D widgets. So if we combine our results with the ones from 005, we can conclude that shift sliding is globally faster than widgets, regardless if the object is in contact or not. And also, shift sliding with depth pop is 81% faster and 67% more accurate than 3D widgets. And also, 1-view is faster than 4-view, but less accurate. So here's some future work. We could adapt our interaction techniques to touch screens. For example, we can use finger flick for the depth pop actions. We could experiment with back face sliding, so sliding on the back surface of the scene. We could also experiment the use of transparency for positioning of invisible objects. We could also test our methods in VR setups. So in conclusion, we presented 2 new and easy to use 3D positioning techniques, and our user studies showed that our 2 techniques are more efficient for 3D positioning than the standard 3D widgets. Thanks for listening.
Thanks, Junwei. Questions for Junwei? Please step up to the microphone. Remember to say your name and your affiliation.
Hello. My question is, since our company have done an unrelated test a few weeks ago, and we found something interesting with different technique that user with prior experience with 3D modeling tool and user or novice user have performed very different conventional, traditional way to manipulate object. So would you, and I see your paper that you have 5 students has some gain experience for the participant. So do you consider test that with people with 2 different groups? Like some people has very good on manipulate 3D modeling in traditional way, and some novice user. Do you consider that will make impact with the performance?
Thanks for the question. So both of the studies we did, we used novice users, so they don't have like professional 3D editing experiences. But I guess it would be interesting to see like how our technique will help experienced users, because we got some feedback from the users, and they said, okay, they have used like 3D modeling software before, but they're not experts. So they told us that it would be nice to have those features in, for example, Maya or like 3ds Max. So it would be interesting to see if like our technique would help like both novice and expert users.
Nicholas Katsakis with the University of Hamburg. Thank you for your presentation. I think this is a very interesting work. I tried the demo yesterday and I thought it was great. My question is, so the sliding technique looks at, if I understood it correctly, it looks at all the geometry of the object to calculate the intersections. Is that correct? Yeah. So if you have an object that has complicated geometry, I wonder, do you have some ideas of how this could work? For example, I'm wondering if the performance would be the same. You showed some performance data with a lot of polygons, and then I also wonder, when you're doing the depth pop, if you have some complex geometries moving in depth across some other geometries, if that would also work well.
Okay, thanks for the question. I think the basic sliding would work well for complex geometries because we only care, well, there could be multiple layers in the scene, but we only care about the layers that are like behind our object. So like there could be multiple layers even further, but we don't have to care about those. We don't have to calculate all the layers behind. So we only care about the closest surface of the scene. So I think basic sliding would work well for complex geometries, but we did have some difficulties for depth pop working in like too complicated scenes, because with StepStop we have to calculate basically all the layers, like almost all the layers in the scene, because it's not enough to calculate just the front few layers, because the object may not just fit in those layers. So basically with more complicated scenes we need much more computations, and that's why we are planning to optimize the depth pop algorithm. So it would hopefully it would eventually work for more complex scenes.
Even the sliding, I can imagine sliding a very complicated object in between, I don't know, two other objects, and then accidentally popping on top of it. So this might be, an interesting future work for you guys to look at how you could do that.
Yeah. Thanks for the suggestion.
Thank you.
Let's thank our speakers.